Okay. Uh, it is my pleasure to introduce my friend Professor Tin-Yau Tam. He is the department chair at University of Nevada. His research interests includes metric theory, multilinear algebra, numerical range, and Lie groups. He is an editor of some prestigious journals in linear algebra, such as Linear and Multilinear Algebra, Electronic Journal of Linear Algebra, and Special Matrices. According to Tetrablock Math, he has published 110 papers, several of which have had impact on the works of many mathematicians. The title of his talk in this seminar is Geometry and Inequalities Associated with Symmetric Space of Non-Commutative Type. Professor Tam, please. Professor Tam.
Okay.
Can you hear me? Dr. Salemi? Okay.
Can everybody hear me? Oh, very good. Okay. I appreciate a lot of people respond saying yes, they can hear me. So now I'm going to share my screen. Can you see my screen? No response, not sure whether you can see my screen or not.
Yes, we can see it.
Should I go ahead?
Yes. Yes, we can. Please go ahead. Can you hear me? Professor Tam, can you hear me?
Yes, Professor Tam, Tin-Yau, please start your talk. Thank you.
Professor Tam, can you hear me? I'm speaking right now. Can you hear me? We can hear you.
Yeah.
Can you hear me?
Professor Tam? Please start your talk. Dr. Salimi?
Oh, okay.
Professor Salimi?
So I just go ahead. Let me share my screen. For some reason, I can't hear you. Let me share my screen. Okay. I believe you can see my screen. So I just start my presentation this morning. Before I go ahead to do so, I would like to mention that I'm greatly honored to be invited to deliver this talk to you. This is T.Y. Tam from the University of Nevada, Reno. Let me scroll down the screen a little bit. This is John work with my two PhD graduates. One is Elaine Grant, another one is Roy Liu. I believe they are in the audience. So let's move on. All right. So I would like to mention about our PhD programs before I talk about the research today. All right. So we have two new PhD programs in our department at the University of Nevada, Reno. One is PhD program in mathematics, another one is PhD program in statistics and data science. If some of you are graduate student or you want to go to graduate school, and if you're interested in our PhD program, please contact me. For PhD students, if you are excellent, we would provide support. Usually 1 year, we provide almost 20,000 US dollars with significant tuition waiver. Okay, so let me go back to the topic of my talk. Today, I'm going to talk about geometry and inequality associated with symmetric space of non-empty type, non-compact type. All right, so let me start with some basic concept that everybody would be able to understand. The first one is tangent space and curvature. Suppose you have a manifold. If you take a look of the picture, this M is a manifold, and Tm, this is the tangent space of M at the point X. All right. Oh, I mute my speaker. 1 second. Mute my speaker. Okay, I just mute my speaker. All right. Now, you have the manifold. You have the manifold, you have the tangent space of the manifold, and you have a curve, gamma t, passing through the point x, and you have a velocity vector, or some people call it the tangent vector. And so that's the concept of tangent vector. And if you take a look of the other picture, you have a curve on the plane, and then you have a point P, all right? So there is a tangent line, of course. A tangent line is something like that. And then you can draw a circle. The circle would be best fit at this point to the curve. And this is the center of the curvature. And rho is called the curvature, all right? Or some people call it 1 over rho. And now the curvature reflects some intrinsic property of the manifold or the surface. Say, for example, we have 3 surfaces. One is this one. It's a hyperbolic type, negative curvature, and this is the 0 curvature type, flat here. And this is a positive curvature, or this is a sphere. So the curvature would tell you something about a given surface. For this case, they are all 2-dimensional manifold living in a 3-dimensional Euclidean space. Now let's move on. As I said, the curvature provides important information about the geometric structure of a manifold. In particular, here we are talking about a Riemannian manifold. For example, it is related to the rate at which two geodesics meeting from the same point move away from each other. So what is the interpretation? The lower the curvature is, the faster they move apart. And many important geometric and topological properties are implied by suitable curvature conditions. However, I have to say, curvature is usually not easy to compute explicitly. In the case of a Lie group equipped with a left invariant Riemannian metric, John Mueller obtained an explicit formula for sectional curvatures, but it is still quite complicated. Although it simplifies in many special cases, we have not seen a simple formula for the sectional curvature on the general linear group of matrices, even that. That is valid for all sections. So let's talk about covariant derivative. So these are the basic stuff or preliminary material for Riemannian manifold, in particular Riemannian metric. And you can imagine that at each point there is a tangent space. All right, so this is T of G. So this is the Lie group, and this is the tangent space. And this is a given point G in the big G. And the metric is called left invariant if this condition is satisfied. That is, you can, through the left translation, move the 2 points X and Y respectively. All right, a left invariant Riemannian metric on G is completely determined. All right, someone is talking. Okay, a left invariant Riemannian metric on G is completely determined by the inner product, and Mueller obtained the following covariant derivative under a left invariant metric. So you can see this formula. Okay, why we have something like the inner product? Actually, this is from the Riemannian metric. All right, and the square bracket is the Lie bracket. Now let's talk about our familiar group, that is the general linear group over R. It also applies for GL and C, not just GL and R. So you can define the Frobenius norm, and then are easily satisfied after some computation. And then you can decompose, all right, the Lie algebra of G, which is the set of all n by n real matrices, into the direct sum of two subspaces. One is S, which is the subspace of symmetric matrices, and A, which is the subspace of skew symmetric matrices. We notice that this is a direct sum. Not only that, it's more than a direct sum. It is an orthogonal direct sum. For any two subspaces G1 and G2 of the Lie algebra G, that is the space of all n by n real matrices, we can denote the subspace generated by this, generated by all Lie bracket, where U is from G1 and V is from G2. And thus you have this condition. This is a very well-known fact among Lie theorists. This is not only true for GL and R, it is true for all semi-simple Lie algebra associated with the Cardan decomposition, but we don't want to make it so complicated. So just focus on the space of symmetric and the space of skew symmetric real matrices, that is S and A respectively. All right, before I move on to show you the formula, I would like to point out there is a very interesting phenomenon. That is the relationship between GLNC and its tangent space. The tangent space, if you can see that, this is like a surface, GL and R. And, oh, I should say GL and R. Okay, but I use R to illustrate the idea. So you can see that this is a tangent space, and this is a curve. So there's nothing wrong with it. Everything looks normal. But as a matter of fact, this photo is highly deceptive. The reason is GL and R as the tangent space of the big GL and R is supposed to include the big GL and R, because this is the space or the algebra of n by n real matrices. And this is the space or the group of n by n real non-singular matrices. So indeed, we know that the tangent space here contains the surface. So this picture doesn't reflect the reality. And why this is the case? Because according to our intuition, tangent space should not like that and should not contain the manifold itself. Well, that's our intuition. But sometimes reality may conflict with our intuition. All right, so this is and it also reflects the topology of the group GL and R is very complicated, at least more complicated than what you thought. So if you think you have a good understanding of both GL and R here, or this little GL and R, think twice. All right, and this is the definition of sectional curvature, which is defined this way. Okay. So you can use the forbiddenness norm to do it, and this is the curvature tensor. And then there is a sectional curvature, which is defined like that. The denominator is always positive because we pick two linearly independent vectors, u and v. And the denominator is indeed the area of the parallelogram determined by u and v. All right, so the sign is the same as RUVVU, all right, this sectional curvature. And here is the formula, all right? So if you want to compute it, well, of course, it takes some time to get to this formula, all right? In particular, if you focus your attention on S, that is the space of symmetric matrices over R, or the skew symmetric matrices also over R, you get this. They are extremely simple. That is, when you have U and V, if you pick U and V from S or from A, both, then you get this formula and this formula respectively. But if your U and V are not necessarily both in S or not necessarily both in A, then this is the general formula. Okay, it's in a very recent paper with my PhD student, Elaine, my colleague at Auburn University. All right. All right, next, we'd like to mention that Pn is a Riemannian manifold. Well, in the previous slide, you saw the sectional curvature. But here I would like to stress that it is a Riemannian manifold. And the next thing I would like to talk about is the geodesic. So let's start with Pn, which is the set of all n by n positive definite matrices. You can view it over R or you can view it over C, if it doesn't matter. But let's say it is over R. So the space is equipped with the following Riemannian structure. So you have two tangent vectors, x and y. Both are tangent vectors to the manifold at the point P. All right. So you can imagine that you are taking inner product between x and y, but not everywhere, but at the point P, and this is the formula. So all P, x, and y play some role in this formula. And if you draw a curve, gamma, this is a curve on Pn, the space of positive definite matrices. The arc length is this, okay? All right, it takes a little bit of time for you to get this formula. All right, and the Riemannian structure would turn Pn into a metric space. This is it. Well, DAB and DBA are the same, because if you swap A and B and you take eigenvalues, you don't have much difference, okay? All right, so you get the same expression, all right? So let's move on, all right? So Hn is the space of all Hermitian matrices, or you can say symmetric matrices over R, Hermitian over C. And Pn is the exponential of Hn, all right? So you have similar thing, but the topology is also odd as well, because Hn contains Pn, the manifold. Hn is the tangent space, but Pn is the manifold. Here is the identity matrix. All right, so the topology is interesting. All right, so of course it would affect the exponential map as well, or it reflect the interesting property of the topology. So let me give you a very simple example. Suppose we talk about SL2R and SP2. What is SP2? That is all positive definite matrices 2 by 2 over R, but with determinant 1. Because there is no way I can draw a picture for high dimensional space. So this is it. All right, so this is a set of all 2 by 2 matrices, positive definite, and the determinant is 1. So this is the determinant. All right, which can be identified with a set in R3, because you can delete one Z here. So you have X, Y, Z, and then you can draw a computer picture. Don't get me wrong, you only take one piece of this picture because it has 2 sheets. You only take one sheet. If you like, take the up half, okay? All right. So this is the geodesic formula obtained by Bartia and Holbrook back in 2006. And the geodesic is you need. So if you have 2 points A and B in Pn, and how to write down the formula for this geodesic or equation, and here is the formula. This is the formula. So this is the famous geometric mean, or the T geometric mean formula. All right. It doesn't look natural, but that's the way it is, because matrix multiplication is not commutative. And this is the distance between A and B. So you can recall what you have seen beforehand. And there is an inequality. So I draw a picture here. So you can imagine that this corner is A, another corner is B, another corner is C. This is kind of a triangle, the geodesic triangle. So you can see that the inequality reflect what happened on the geodesic triangle. So let me further explain what actually happened of this inequality by Bartia and Holbrook. On a flat plane, you have similar triangle. So if you have A, B, C, and you retract from C to D, retract from B to E, the same rate. So this should be 1/2 of that, okay? All right. However, if you do exactly the same thing on another triangle, which happens to be the hyperbolic triangle, that is a triangle sitting here. So when you retract, all right, you don't get the equality or the ratio 1/2 or something like that. So instead of equality, you only get this inequality, and T is there. So T could be 1/2 if you retract 1/2. Or it could be 1/3 if you retract by the rate of 1/3, okay? But you don't get equality, unlike the plane triangle here, all right? So this also reflects that the geometry is not Euclidean, it is hyperbolic. All right, symmetric space. Well, as a matter of fact, the geodesic formula obtained by Bartia and Holbrook has been known a long time ago. Indeed, this is not only true for Pn, it is also true for symmetric space, G mod K, and I will say a little bit more about symmetric space later. But at least at this point, you just imagine that Pn, that is the positive definite matrices, Z is a prototype. All right, so symmetric space P is a generalization. So you can see all this formula, okay? All right, and you have the norm here, all right? And you would be amazed, a long time ago, more than 80 years, Siegel already obtained that, okay? At that time, he didn't fully obtain the symmetric case, the symmetric space case, but Colston got it, all right? He didn't, I believe in his paper he mentioned this, okay? In particular that. I don't remember exactly this form is given. But anyway, in our recent paper, we mentioned all this. Okay, so we call that Barty and Holberg's formula compare distance. Let me go back. You see, this is a distance between B and C. This is distance between the halfway. That is the T halfway. All right. But we are talking about more. As a matter of fact, this observation was given by Colston. He considered the tangent vector. That is, instead of talking about, let's see, go back here. Instead of talking about the distance from this point to a point somewhere here, and the distance from this point to a point somewhere here, he considered the tangent vector starting from this point on this curve, and another tangent vector starting at this point to this curve. And then he made comparison. Of course, you can do similar thing on this side. All right. And then this is the concept. So just keep that in mind. We are talking about tangent vector. But how can you compare tangent vector and why it is related to Bartier and Holberg's inequality? Well, here is the relationship. XRS is the tangent vector from the point R to the point S. If you take the norm, which is induced by the Killing form, which is exactly the distance between R and S. Here I identify the symmetric space with P, or vice versa. All right. So as a general property, Colston obtained this nice relationship. And this order is called the Colston order. Because of the time constraint, I have no time to further elaborate that. All right. But anyway, you can see that this, why Colston would like to study this, because Colston noticed this property, which is a property of a hyperbolic space. All right, so he went furthermore and obtained this generalization. So the inequality for the scalars, because these two are scalars, the inequality here is replaced by the P order. All right. And then later, we focus on Bartier and Holberg's inequality. We obtain this one. So this is a direct generalization of Bartier-Holberg's inequality. Not just lift it up to the symmetric space, but change the scalar inequality to Colston P order. So if you consider the length on both sides, you will get something like that. Okay, all right. So that's a corollary. All right. Another thing I would like to mention is semi-parallelogram law that my PhD student Elaine and I obtained last year. So if you have a geodesic triangle ABC, and M is the midpoint of the geodesic, here is the picture, then you have this inequality. The semi-parallelogram law, say for example, in many differential geometry book, or in Bartier's book, I think it's called positive definite matrices, all right, would give you this inequality, all right. As a matter of fact, Pn is only a special case. This parallelogram is true not only for Pn, it is true for all symmetric space. For a complete Riemannian manifold M, the semi-parallelogram law holds locally, right here, okay, all right. And if and only if M has a non-positive curvature, And the symmetric space that we have talked about has negative net curvature, so we are good. All right. So on the other hand, there is a so-called Morse-Thal distant comparison theorem. Here we go. All right. And then it turns out that Morse-Thal's inequality and semi-parallelogram law are identical. Oh, sorry, there is a question mark. I think when I latex it, I forgot to latex it twice. So this is true. So that is Morse-Thal's distant comparison theorem implies the semi-parallelogram law. So we finished the other direction. All right. And as a matter of fact, one can deduce a number of matrix inequality from the above inequalities. And we don't have time to work out those little details, but I know that because I work out some of them. All right. Say, for example, if you focus SUNN, you get quite a number of inequalities for contraction matrix. So you generate a family of inequality. If you talk about SPNR, then the corresponding inequality would be for accretive matrices. Okay, let's talk about a result, which is a result of So. So and Thomson back in 1991 conjecture, and So himself proved the conjecture, and the following is the theorem. So if you start with two Hermitian matrices, X and Y, and you take the exponential, X over 2, and then E to X, Y. Of course, you get positive definite matrices. These three are positive definite matrices. And then you take the product that way, and you get a positive definite matrix. And then you take log. Of course, you will go back down to Hn. It turns out that this is indeed in the sum of the two orbits, all right, of X and Y respectively. And the orbit is under the conjugation action of the unitary group UN. And the problem is related to the sum of n by n Hermitian matrices with prescribed eigenvalues. That is the famous A plus B is C problem, okay? And so use a result here, all right, Kolyabov, all right, in order to get that, all right? So a heavy machinery has been used in order to deduce that. And I'm going to extend those results, all right, and tell you how to do that. It is the Lie setting. You have a non-compact connected semi-simple Lie group with Lie algebra G, and you have Cardan involution. And K is the fixed point of the Cardan involution, which is the big theta. And then the little theta is the defensor of the big theta, which is the Cardan involution on the algebra level. And then you have the algebra level Cardan decomposition, and you have the killing form and things like that. And you can decompose K and P as an orthogonal sum because now you have a bilinear form. All right. So this is the extension. We have Cardan decomposition. So each G can be factored into two components, P and K. All right. P is in P and K is in the big K. And here is our generalization. We also make use a very powerful result, okay, almost, well, 20 years ago, all right, and a relatively recent, but still 15 years ago, all right, 2005, in order to arrive at. So this is true not only for positive definite matrices or Hermitian matrices, it is also true for the Lie setting, right? Next, it's still about the geometry. So this is the geometric mean. Okay, let's make it simple. Let's talk about Pn. And what I'm going to say actually is true for all symmetric space, but I don't want to use all those fancy terms. So this is the geometric mean. This is called the spectral mean. Geometric mean and spectral mean were introduced by these famous mathematicians. All right, and you can check some simple properties. All right, they are not difficult to see, just simple computation. I think the first paper is more well known than the second paper. Fitter and Pitak's paper is less well known compared with the first paper. but this is a good paper. I would encourage you to read that. It has quite a number of nice results. The geometry may not be fully disclosed in the paper, but they involve a lot of algebraic manipulation. And then here we go. So it is related to those results. So you have sharp, this is the geometric mean, and you have natural, this is the spectral mean. All right. And why this is called the spectral mean? Because this guy, if you take the square, is similar to AB, and thus they share the same set of eigenvalues. So that's why it's called the spectral geometric mean, according to Fiedler and Pitard. So this is the result. All right. And then very recently, we obtained that. That is, this is true for the symmetric space. Okay, now let's extend it a little bit. That is, we talk about the T geometric mean and we talk about the T spectral mean. The T spectral mean was introduced by 3 Korean mathematicians, An, Kim, and Lim. All right. As we point out, the T geometric mean is interesting because of their connection with the Riemannian geometry. As we point out before, this, if you equip with a suitable Riemannian metric, the curve is the unique geodesic joining AB in Pn. However, I would like to point out that the corresponding counterpart for the spectral mean is not the geodesic joining A and B, because number one, the geodesic is unique. So this is the geodesic. And here we have another curve also joining A and B. So, and these two are not the same. All right. And thus this cannot be the geodesic with respect to the same Riemannian metric. All right. And there is an inequality called the Golden-Thomson inequality. Look at that. It is related to the geometric mean and the spectral mean. All right. And Kim and Lim obtained this one. As a matter of fact, the first inequality was first obtained by Hire and Piss as the complement to the celebrated Golden-Thomson inequality. All right. And the second inequality is actually a refinement of Golden-Thomson inequality when R is in between 0 and 1. Okay. So we call that Pn can be equipped with a suitable Riemannian metric. So the curve is the unique geodesic joining A and B. When T is 1/2, usually we write this way. That is the midpoint. All right. Now we are going to discuss some geometric properties of both geometric mean and spectral mean. First, in the space of Pn. They are also true in the context of symmetric space, but we don't want to spend time too much on the symmetric space. So let's start with matrices, Hermitian matrices, X and Y. And R is a given integer. So you have phi of R and you have psi of R. Define it that way. Both are related to the geometric mean and the spectral mean, respectively. And the following 4 statements are true. Some are known. Say, for example, this is known. All right. This is also known. Okay. So you can check the literature and all right. So in particular, this one, the trace function of that is monotonically decreasing on R. All right. And the other one is increasing on R. All right. So they display different behavior. I mean, geometric mean and the spectral mean. Okay, so here we have some formula. I just pull out some formula from our recent work. Look at this one. If you are given 2 points, say for example the symmetric space, if you don't like symmetric space, you can think of it as positive definite matrices. So we have this formula. We have this formula. Okay, if you take a look at the left side, say for example the first one, it is a point, or you can interpret it as a curve. And this is another point, all right? Or more general, you have that. Okay, get that. So let me try to illustrate to you one by one what it means and its significance. So let me draw a picture. All right, now this is the left side of the first formula, and this is the right side of the first formula. So you can imagine that this is the starting point P, and this is Q. You join P and Q through the T geometric mean. That is the geodesic. So you start from P, and you move towards Q, but you stop there at time T. After you stop there, you take a break, and then you keep moving, and you move on. This is the starting point. And you still move towards Q. You don't change your destination. Your target is still Q, but this time you travel S over 1 minus R time unit. So you reach this point. In other words, trip 1 is from P to this point, and then to that point. So you have 2 separate trips, and you composite them together. The outcome is exactly the same as you travel from P to Q, and you stop when time is R plus S. That's the meaning of this formula. Is it okay? Next, the second formula. Well, tell you the proof of the first formula. It's not difficult. As a matter of fact, because geometry is on our side, we have the geodesic property. So it conveys some good information. So we can get the conclusion more quickly. And this is it. The path is the geodesic joining P and Q in P, and it meets, all right, this point when T is R plus S. So when R is somewhere here, the path is the geodesic joining that and Q in that, and it meets that. So you can conclude that they are the same. However, let me ask you this question. If you don't know anything about the geodesic, and you want to prove that the left side and the right side are the same without using geodesic property, that means you need to prove this formula. That's the explicit form. I think in terms of algebra, that is not entirely trivial, and it is not easy to prove. So the geometry plays a very significant role here to see that. Well, the next equation. Let me go back to the next equation. If you go back here, this is the second equation. Well, you can see that it's very similar to that one, right? Because you're talking about that, which is the spectral mean. So I don't have to explain it. I just show you the formula. All right, this is the picture. So you travel one trip, the second trip, and then one trip. You get the same thing. All right, so the idea is the same. But now this time, in order to prove it, you cannot use the geodesic property because this curve is not a geodesic. And thus, you have to work out the detail. Okay, I just want to let you know you have to work out the detail for that. All right, okay. But indeed, there is a more general equality behind this. So let me draw your attention. The more general equality is this one. Can you see that? It has 3 parameters, R, T, and S. 3 time parameters, 2 points, P and Q. And so this is the picture. All right. So let me try to illustrate what it means. On the right side, it is not difficult. That is, you start from P to Q, and you stop when this is the time. The time is 1 minus T times R plus T times S. But how about the left-hand side? Well, if you take a look at the left-hand side, it means the following. You start from P, towards Q, stop at R. So this is your first term. How about this one? You start with P towards Q, and you stop S. Where is it? But the thing is, it is the same as you start with Q and stop at the time 1 minus S towards P. So that's the point. Actually, this is the point. So now you have 2 points, point 1 and point 2, and then you composite them. That is, this point is moving towards this point, but stop at time t. And the outcome is the same as that one. That is, you don't have to do so complicated thing. That is from P to Q directly and stop at this time, 1 minus t times R plus Ts. Is it okay? Next, the proof is not trivial, as non-trivial computation is involved. And you can imagine the explicit form is very complicated, all right? But we managed to prove it. And I have some questions for you before I end my presentation. Number 1 is the T spectral mean curve joining P and Q are geodesic under some suitable Riemannian metric. The key word is suitable. That is not the existing one. We don't know this is true or not. If the answer is yes, what is the metric? Can you provide a metric? All right. Of course, under this metric, the usual geometric mean would not be the geodesic under this metric. And we have a conjecture that we want to compare the geometric mean and the spectral mean. All right. We conjecture that this relation holds. At least when t is 1/2, this is true. Okay, we're still working on it. I know if this is true, a more general statement is true. That is for symmetric space with respect to Costan's p order. Okay, all right. I can get it done by using representation theory if this is done. All right. So I think I better stop here. Thank you very much. All right, this is my first time giving such an online invited talk. So if there are some glitches, things not perfect, please let me know. Thank you very much.
Thank you very much, Tam, for your nice talk. It's Moslehian, and I would like to ask about any question or comments, please.
Oh, I can turn it back on, the speaker. Can you hear me? Can you hear me?
Can you hear?
Okay.
Professor Tam, can you hear us?
Any question or comments, please? Okay, it seems that we have some connection problems. Professor Tam, thank you very much for your talk. Okay, and thank you the audiences also.
Oh, okay. All right. If you can hear me, the results are in the 2014 paper of Liu, Liao, and me. So just send me an email, and I'm more than happy to send you the paper. All right. Let me give you my email address through the chat. All right. Thank you very much for listening my talk. I wish I could see all of you.
Thank you very much, Professor Tam and Professor
I
Muslihan.
can't hear you.